This slide deals with a liquid where a dissolved gas is consumed in a zero-order reaction. This could be oxygen being consumed in one of the last stages of water purification, where the limiting factor is availability of organic material, not oxygen. The gas above the liquid is assumed to be in equilibrium with Ca(0) in the top surface of the liquid. This means that the diffusion in the gas phase, and the dissolution and ejection of gas, A, at the liquid surface, occurs at much higher rates than the diffusion of gas, A, further into the liquid due to this gas being consumed. The gas consumption occurs at a uniform and constant rate of K0 moles per cubic meter per second, throughout the body of liquid, B. At the bottom of the liquid, just above the impermeable boundary, there is no diffusion of the dissolved gas, hence, dC, A, by dy, will be zero as well, from Fick's law. Note that a gradient of the dissolved gas will always produce movement of the gas down the gradient. Consider a small increase in depth, dy, from y to y plus dy. You have the gas diffusing into it at a rate of n dot a in mole per second. Then you have the consumption of some of the gas between y and y plus dy. K0 is in mole consumed per cubic meter, so you need to multiply it by the volume of the liquid between y and y plus dy to get the mole per second consumed. This volume is the cross-sectional area of the tank, times dy. The flow rate out is equal to the flow rate in, plus the slope of the rate of diffusion, times dy. This is basically equal to the change in molar flow rate, d, n, dot, a. Note that the slope is negative due to the consumption of gas, and hence the change in the flow rate is also negative. In the equation, n, dot, a, can be cancelled out both sides. After that, dy can also be cancelled out on both sides. In the equation, n, dot, a, can be substituted for Fick's law. The cross-sectional areas cancel out, while the diffusivity can be taken out of the differential, as it is constant. The resulting equation is known as the mass diffusion equation, which can be integrated twice to give the concentration profile. The first integration is from the bottom of the tank to a position y in the tank. The bottom of the tank is chosen as you know that d, c, a, by d, y, is 0 where y is equal to L. The expression of d, c, a, by d, y, can be integrated again, this time for the top surface to a position y in the tank. The top of the surface was chosen as you know that this is where the concentration is, Ca(0), a value that can be calculated using the equilibrium constant for the dissolution of gas A, and the partial pressure of A. In a way similar than that for heat transfer, to get the rate of mass transfer across a flat plane solid, you need to integrate Fick's law in the direction of mass transfer, from position y1 to y2, which also corresponds to a concentration of Ca1 and Ca2 respectively. If the molecule source on the left-hand side of the flat plane has been supplying a steady rate of A molecules, while the molecule sink on the right-hand side has been removing the molecules at the same rate for some time, N dot A will be constant. The system will be said to be at steady state. This is Fick's law, which you can apply to diffusion in solids and liquids as well. You can integrate this from y1 to y2. At y1, the mass transfer area will be the big surface turned away from you, and is equal to breadth times height. Even at y2, the mass transfer area, here turned towards you, is also b times h. The mass transfer area remains b times h at any position between y1 and y2. You can take the mass transfer rate, the diffusivity, and the mass transfer area out of the integral signs, as they are constant. The integral of dy is y, and of dCA is Ca. Integrating between the limits of y1 and y2, which correspond to concentrations of Ca1 and Ca2, you get the following. You can make N dot A the subject of the formula again. You can rearrange the equation to get N dot A in terms of R, M, the diffusion resistance. You can regard Ca1 minus Ca2, which has a positive value, as the driving force for the mass transfer. From R, M, the mass diffusion resistance, you can see that if the solid is thicker, and y2 minus y1 is larger, the resistance to mass transfer will be higher. However, if the diffusivity, or the mass transfer area, is higher or larger, the mass diffusion resistance will be lower. This makes sense, does it not? You can also develop the mass diffusion resistances for other solid shapes in this way, integrating with respect to R instead of Y, as you can see in the following slide. The diffusion resistances of three different geometries are given in the last column.